Hello everyone. In the first video, we talked about the Laplace transform. In this video, we will talk about the inverse Laplace transform. In the first video, we talked about if we have a signal x of t and we did the Laplace transform, we get x of s, which tell us a lot about the frequency content of the signal x of t. Now let's assume we did all kind of processing to this x of s and we want to get back the signal in the time domain so we can hear it or watch it. So to do that we need to do the inverse Laplace transform. Well, first we take the signal x of s and we break it down to a simple function such that this function or this one will be one of these functions in the table. And then we use the table to go back from x of s to x of t. And how do we break these signal to a simpler signals? We use the partial fraction expansion. So let's look how the partial fraction expansion works by examples. So let's assume you have a signal in the Laplace domain x of s. And I want to know what does it equal in the time domain. So we need to find x of t. So the first step is to factor out the denominator. So this will be x of s equal. And in the denominator, I will factor it out s plus 3 times s plus 2. Now I can make this term equal a over s plus 3, which is this one, plus b over s plus 2. Now the task is to find what is a and what is b such that if I add these two terms, I will get the original function. And there are different ways to do it. A simple way is if I want to find a, I will multiply every element here and here and here by its denominator, s plus 3. And then set s to equal minus 3. So only this will survive, this will disappear. Then I will have a function that has only one unknown, which is a, and solve for it. So let's do it. So to find a, I will multiply everything by its denominator, s plus 3, and then I set s to equal minus 3. So if I do that, then 7s plus 6 times s plus 3 divided by s plus 3 s plus 2. And here it will be a times s plus 3 divided by s plus 3. And again here b s plus 3 divided by s plus 2. Now s plus 3 will cancel here, s plus 3 will cancel here, and I will have 7s plus 6 over s plus 2. And here I will have a, and here b s plus 3 over s plus 2. Now if I let s equal minus 3, that will be minus 3 plus 3 will be 0. So this will go to 0. And I will end up with 7 times minus 3 plus 6 over minus 3 plus 2 equal a. And from here, a equal 15. Now, if I need to find b, I can multiply everything here by its denominator, which is s plus 2, and then set s to equal minus 2. So to find b, multiply everything by its denominator, s plus 2, and then set s to equal minus 2. And if I do this, then it will be 7s plus 6 times s plus 2 divided by s plus 3 times s plus 2 equal a times s plus 2 divided by s plus 3 plus b s plus 2 divided by s plus 2. Now this will cancel this will cancel this, and now if I set s equal minus 2 here and s equal minus 2 here, I will get the following. This will be 7 times minus 2 plus 6 over minus 2 plus 3 equal. This when you put for here minus 2 plus 2 is 0. so this will be 0, and here I will have only b, and from here b equal minus 8 over 1, so b equal minus 8. Okay, so I found a, I found b. Now let's go back here, and this problem here, which is the same as here, now this is equal a, which is 15 over s plus 3, plus b, which is minus 8 over s plus 2. Now the inverse Laplace transform of this one is x of t. The inverse Laplace transform of this one is the same as this one. Now these terms is very simple. We have it in the table, which is this one. So we're gonna use this one. Let me just write it here. E lambda t u of t, it is s minus lambda. So for this one, if I compare this with this one, here lambda equal minus 3. And for this one, if I compare it with here, here lambda equal minus 2. So the inverse Laplace transform of this one will be 15 e lambda, which is minus 3, t u of t, plus minus 8 will be here, 1 over s plus 2, so that would be e lambda, which is minus 2, t u of t. And that's the answer. Plus time minus, you get negative, so that would be just negative. And when you do the partial fraction expansion, make sure s in the denominator is to the power higher than s in the numerator. Now what happened if in the numerator s to the power similar to the denominator or even higher? Then in this case you have to do long division to reduce the power of s in the numerator to be lower than the power of s in the denominator. So let's take another example here. Okay, so use partial fraction expansion to find the inverse Laplace transform of this function h of s. That could be the transfer function of a system. And we need to find its impulse response, h of t. So we need to do the inverse Laplace transform. So the first step is we have to do a long division to reduce this power to be less than the power of s in the denominator. So one way to do that, you can do it by a long division divided by s squared. And if I multiply this by 2, 2 times s squared, it's 2s squared. 2 times 3s is plus 6s. 2 times 2 is 4, plus 4. Now I will change the sign and then I add them up. So this will be 0, plus 5 minus 4, that is plus 1 minus 6s. So then this I can write it as 2 plus this term divided by this term. So that is 1 minus 6s divided by s squared plus 3s plus 2. Now I can carry out the partial fraction expansion of this term to simplify it further, because s in the denominator is to a higher power than s in the numerator. So let's do the partial fraction expansion of this term. So this will be then 1 minus 6s over s squared plus 3s plus 2 is the same as 1 minus 6s over s plus 2 times s plus 1. And this is the same as a over s plus 2 plus b over s plus 1. And to find a, I will multiply both sides of the equal sign by s plus 2 and then set s to equal minus 2. So this will be 1 minus 6s times s plus 2 over s plus 2 times s plus 1. And I set s to equal minus 2 equal a times s plus 2 over s plus 2. And again you set s equal minus 2 plus b times s plus 2 over s plus 1. And you set s equal minus 2. Now this will cancel this and this will cancel this. So you have 1 minus 6s over s plus 1. Here it will be just a. Here you cannot cancel numerator by denominator, and when you plug for s here minus 2 plus 2 is 0. So this will go to 0. So that will be plus 0. So from here, a equal 1 minus 6 times minus 2 over minus 2 plus 1, and this will be 13 over minus 1, that's minus 13. And the same thing, if I need to find b, I just multiply everything by its denominator, s plus 1, and I set s to equal minus 1. So that will be 1 minus 6s times s plus 1 divided by s plus 2 times s plus 1 equal a s plus 1 over s plus 2, and you set s equal minus 1 plus b. Now this will cancel here, this will cancel here. Here s plus 1 cannot cancel anything in the denominator, and when you set s equal minus 1, this will be minus 1 plus 1, 0. So this will go to 0. And this will be 1 minus 6 times s, which is minus 1, divided by s is minus 1 plus 2, equal b. And from here, b equal 7 over 1, which is 7. Okay, so we found what is a and b. So this equal sign will be 2, and this term here is a over s plus 2, so that is plus a is minus 13 over s plus 2 plus b, and b we found is 7 over s plus 1. So all we did, first we did a long division and we got these two and this one. Then we did a partial fraction expansion and we got this one. So that's h of s. Now we do the inverse Laplace transform, and this is h of t, and we use the table. That 2, it's in the table here. We have x of s, when it's 1, the inverse is an impulse. So we have 2, then it will be 2 times the impulse. Minus 13. This now is 1 over s plus 2. Again, from this table. So this will be e minus 2t u of t plus 7. So that's 7. 1 over s plus 1. Here is lambda minus 1. So that will be e minus 1 t u of t. And that's the answer. That's the impulse response of the system. Okay, let's take one more example. Cover all cases. In this case, what if when you factor the denominator, you end up with a complex, something like this. So I can factor out these. First, in the denominator, it's s cubed, which is higher than power of s in the numerator. So I don't need to do long division. So I can express this as k1 over s plus, and when you factor these, you will get something like this. S plus 5 minus j3 times s plus 5 plus j3. This is like 5. And let's say this is a. And if you factor this further, you will get this. k1 over s plus k2 over this plus k3 over this. Now when you get this one, it's not a good idea. If you factor out a polynomial and you get complex roots, then don't factor it, because to do the inverse Laplace transform of these is gonna be many steps. So best is to do the following. This s, it's okay, we can factor out this k1 over s here, but then these we will keep it the same. But always, if you have in the denominator s squared, then express it this way in the numerator, as plus b. If I just ignore this term as and they just make it b, then when I add these two terms, I will end up in the numerator s squared, which doesn't exist here. Now the question is, how do I find k1, a, and b? K1 is very simple. I will just multiply everything by s and set s to 0. Let's do it. So this is 6s plus 34. So to find K1, multiply everything by S and set S to equal 0. So in this case, this will be 6S plus 34. Now set S to equal 0. Now this S will cancel here. Now this S here will not be canceling anything in the denominator. So the whole thing will be 0 when you set this S to 0. So then you will have here 6, 0 plus 34 over 0 plus 0 plus 34 equal K1. And from here, this will cancel here, so you get K1 here. And from here, K1 will be equal 6 times 34 divided by 34, so that is 6. Okay, so now the question is, how do I find A and B? There is different way to do it. One way is I plug for S one value like 1 and I will get one equation and two unknown A and B. Then I plug another value for S, maybe 2, and I will get a second equation and two unknown A and B, and then solve these two equations. So that's one way. Another way is I multiply every term here by this denominator. Then I will get one equations. Then from this one equation, A and B can be solved to make this equation true. So let's do that. So I'm gonna multiply this term by its denominator, this term by this denominator, and this term by this denominator. So then I will get 6S plus 34. When I multiply this term by its denominator, the denominator will disappear. Equal. Here, if I multiply it by this S will cancel this, and I will end up with K1 S squared plus 10S plus 34. Now when I multiply this one by this quantity here, this will cancel this, and I will end up with plus AS plus B times this left S. And I can simplify this 6S plus 6 times 34 equal K1. I already found it to be 6, so that would be 6S squared plus 60S plus 6 times 34 plus AS times S, that is AS squared plus BS. Now this 634 will cancel this one, and I will bring every term that does not have A or B to the left of this equal sign. So that will be 6S plus 6S squared will come minus, and this will come minus 60S equal AS squared plus BS. One more simplification. I can write this as minus 6S squared. Here I have 6S, here I have minus 60S, so that would be minus 54S equal AS squared plus BS. For this to be true, A has to equal minus 6 and B has to equal minus 54. Okay, so I managed to find all these values. So K1 is 6, A equal minus 6, and B equal minus 54. So what's the next? Well, we can recognize this is in the table, this equation, which is this term. So if I have h of s here, then the inverse Laplace transform of this. And r here is this one in terms of all elements here. And theta here is this one. And I can find it from all parameter that is here, no one. And b, this one is this, and I can find it from all parameter in this one. So let's bring our equation to here. So it will be easy to solve. Okay, so to find the inverse Laplace transform of this component, we're going to use this property in the table. So by comparing, in our case, A equal minus 6, B equal minus 54, 2A here equal 10. So little a equal 5, C here equal 34. Now we need to calculate B. So B will be square root of C, which is 34, minus A squared, 25. So that's square root of 9. So that is 3. Now to find theta, it's tan inverse 1. Capital A is minus 6. Little a is time 5 minus 54 divided by capital A, which is minus 6. C is 34 minus 25. And if you calculate this one, theta, using your calculator, you will get 126.9 degree. Why am I calculating this? Again, because that's my answer. The inverse Laplace transform of this one is this. So I need to find R, A, B, theta. So now let's find R. R will be square root of capital A square, so that's minus 6 square, times C 34 plus B minus 54 square minus 2 times minus 6 over 34 minus 25. And if you calculate this, you should get 10. So the inverse Laplace transform then of this one will be this one. R, which is 10, e to the power of minus a, little a here is 5, so that will be minus 5 t, cosine b, in this case we've calculated b here to be 3, t plus theta here we calculated to be this one, u of t, which is this. So that is the inverse. Okay, now what about here? 1 over s or 6 over s. Well, from the table we know that 1 over s, the inverse is u of t. So then this one, the inverse will be 6 u of t. And that plus is here. And that's the answer. So this is the expression of x of s in the time domain, x of t. So far we covered 3 examples. When we have distinct roots like this one, that means you factor it out and you got s plus 2, s plus 1, and you need to do a long division. And this example, when you factor it out, you get s plus 3, s plus 2, different roots, lambda. And this third example, when you factor out and you get complex root, like this one. The last example or possibility is when you have a repeated root, s plus 2 to the power of 2. It will be a mistake if you think, oh, this is just k1 over s plus 1 plus k2 over s plus 2 squared. If you solve this one, you will end up with, in the numerator, s squared that is not here. Or you may find a solution k1, k2, but it will not satisfy all possible values of s. So whenever you see a repeated root here, like s plus 2 to the power of 2, you have to have in the denominator s plus 2 and all lower possible power, s plus 1. So if you have here to the power of 3, then you will have here k4 s plus 2 to the power of 3, and the 2 and the 1, all the way to the lowest power. So in this example, we just have s to the power of 2. So to factor out this, then it will be k1 over s plus 1 plus k2, a constant, s plus 2, and all the way to s plus 2 to the power of 2. Now we need to find k1, k2, k3. Again, there are several ways, but the easiest way is, let's write this here. It is plus 10. Now to find k1, I will multiply everything by its denominator, s plus 1, and set s to equal minus 1. So now this will be 8s plus 10 equal, and I set all s equal minus 1 to find k1. Why minus 1? Because this will cancel this will cancel. Now when you set s here minus 1, that will be 0. And again, when you set here s minus 1, this will go to 0. And you will end up with, and k1 will be, in this case, 2 over 1, or k1 equal 2. Now, should I find k2 first, or should I find k3 first? If you think finding k2 first is the right decision, then that means you're going to multiply every element here by its denominator, s plus 2. But that will not solve the problem for k3, because if I multiply this by s plus 2, the denominator of k2, I'm still going to have 1, s plus 2, and that will be a problem. So always find the constant that has a denominator to the highest root first. So in this case, I need to find k3 first by multiplying every element here by its denominator, s plus 2 squared. So if I do this, then set s equal minus 2. 8s plus 10 there is a square here. I'm multiplying everything by s plus 2 squared. And then you set s equal minus 2. When you do this, then this will cancel here. This will cancel this, so k3 will survive. k1, k2 will be set to 0 when you set s equal minus 2. So when I set this to minus 2 plus 2 is 0, so that will go 0. Here, this term will cancel only one of them, so you still have s plus 2. You set this s to minus 2 plus 2 is 0, so that will disappear. So the only thing left is 8 times s, which is minus 2 plus 10 over minus 2 plus 1 equal k3. And from here, k3 equal minus 6 over minus 1, so k3 equal 6. Okay, so what's left is k2. Now to find k2, I can go back to this equation. So I already have k3, I have k1, what is missing is k2. So I'm gonna plug any value for s and solve for k2. Plug value for s, that will make the equation simple, like 0, as long as no denominator will go to 0 when you set s to equal 0. So from here, if I set s equals 0, this would be just 10 over 1 times 4 equal k1 over 1 plus k2 over 2 plus k3 over 4. Plug for k1, here it will be 10 over 4 is 2.5 equal, here k1 equal 2 plus k2, that's what I want to find. k3 is 6 over 4 here. Now I can multiply everything by 4 and solve for k2. So that will be 10 equal 8 plus 2k2 plus 6. And you solve for k2 and it should be minus 2. Alright, we finally found all values for this constant. k1 is 2, so that will be 2 over s plus 1. k2 is minus 2. k3 is 6. And if you use the table, this we already used it so many times, so that would be 2, lambda is minus 1, so that's minus t u of t, minus 2, 1 over s plus 2, lambda is minus 2, so that's e minus 2 t u of t, plus 6, this is new. So if we go back to the table, look for something similar, you will find this. So when you have this square, then you have t. So that will be t e lambda is minus 2 t u of t. And this is h of t. By these 4 examples, we covered all possible partial fraction expansion to find the inverse Laplace transform. Thank you. And next video will be the property of the Laplace transform.